If you are interested to go farther than what we have discussed, then I am here going to suggest you a small project that you can do in your own time. This is not related to your final exam or grading or anything. This is about modeling cooling of electronic chip as 3D transient conduction. We'll build up on previously what we have done with 2D steady conduction, and you will go up to 3D transient. So first start from once again the standard heat conduction equation, and here we have our usual energy equation del T of rho Ct del dot K del T plus Q triple prime. With constant material properties, we take this rho C and K out of the equation. In 3D Cartesian coordinate, this Laplacian will be like this. All these are known to us. And we are here interested about this 3D unsteady equation, where I am taking this alpha here with delta t and writing in this manner. This is my Laplacian. This is the source term divided by thermal conductivity. Alpha is the diffusivity. Boundary conditions could be three types as usual. This Dirichlet type, specified temperature, Neumann type, specified flux, or Robin type, that is convective. Now we come to physical problem. This is where our chip is, which is mounted over a substrate. And you see here the coolant is flowing through this pipe. So this is liquid cooled chip. Now this chip is like a rectangular cross-section solid which is generating heat, and then through convection the heat is removed from this side through this liquid, which is giving a high convection. In other side there is still air and the convection is going on there, but not so much as it is here on this side. So this is once again a case that convection is going on from all sides, but in one side there is more convection, liquid side, and that is how we are going to model it. So let us say that this is our chip, and here we idealize that it's a 3D geometry like this parallelepiped, and it has internal heat generation. It is reduced heat transfer at the substrate side, means this side, and high heat transfer at the liquid side. So this is my liquid side. Here we have high heat transfer. So the way we are modeling it here is that this is my dimension of the chip is this Lx, Ly, Lz, and we are taking this one Lx and Lz is twice L because you have already seen the picture. The base is much bigger compared to the thickness. Actually, it is not too even higher, but this is from the modeling perspective, this would be our starting point. It is insulated at y equals 0, because at y equals 0, it will be difficult to have any heat transfer at all. And then other side, I have at y equals Ly, that means here I have this convection due to liquid, and other side there is still air, so convection to air. So this H1 is due to liquid convection, H2 is due to air convection, and this H2 is less than H1 because the liquid will take more heat. So with this condition, we will solve only 1/4 of the domain as we did before in case of 2D steady conduction. We will taking symmetry boundary condition as these truncated boundaries. And now we will non-dimensionalize the system using our usual dimensionless parameters that we have already studied in case of one-dimensional as well as two-dimensional cases. After we non-dimensionalize, we have our equation. Here this tau is our Fourier number, alpha t by L square, and theta is my dimensionless temperature. Here T minus T infinity, Q triple prime L square by K. I didn't do the BCs here, but I think you already know that how to go about it, and you should be able to non-dimensionalize the boundary conditions as well. You will get BO number, but two different BO numbers will probably get in two places, or you can use one BO number, one H ratio as your parameters. Now, let us summarize this case here. So this is a simple conduction only thermal model for liquid cooled electronic chip. Here you might be questioning that why we are taking it unsteady. Unsteady will give you the idea that what happens to the chip during startup, especially important startup and shutdown, especially startup. During startup, there will be a chance of high heating rate. So that is where we want to see, that is why this unsteady simulation is important here. So from initial transients to how it reaches the final steady state temperature, we are interested in that portion of the chip. So we are studying unsteady heat conduction here. Now to begin with, you can start this from a one-dimensional model. You use the Crank-Nicholson scheme and solve the one-dimensional model. Well, you already have one-dimensional model. You have solved a problem before. But now you include the heat generation in one-dimensional model. Study that, learn from that before going to higher dimensional model. Thank you. That's all for this lecture, and I'll see you in next class.